Forgot.
No worries.
All right, now we're good.
Okay. Excuse me. So yeah, IIT physics. So what's it all about? I mean, we can talk about, it depends on what you guys want to talk about. I can tell you about IIT physics. I can tell you just about physics. I'm a particle physicist, so I could just talk your ear off about particle physics as well, because it's my thing. Yeah, I mean, where do you guys want to start? Do you want to talk physics? Do you want to talk IIT physics? What do you want to talk about?
Just more of IIT physics. What's it like there?
Sweet. Yes. So, yeah, let me tell you about a little bit about the department. So, the program, what we're talking about is about 15 to 16 research active professors. So, as you go through and take your course load, there'll be, you'll be able to, choose from, 15 or 16 different professors who study different topics and who have different research interests and, different experiences with teaching. Now, you would see me if you came to IIT as your intro to the profession, teacher, and maybe as your introductory physics professor, because I teach kind of first semester and second semester introductory physics. Now, I'm going to share my screen because I think that'll help me just talk you through a little bit in terms of expectations about the kind of classes you're going to take as part of your degree. Because at IIT, obviously part of that bachelor's in physics experience is your classwork, right? So part of it's your classwork and your professors who are going to teach those courses. Part of it is your fellow students, right? Your fellow physics undergrads. And so I would say every year as part of physics undergrad, our class, I'd say is between 10 to 25 new physics undergraduate students. So there's obviously a broad range there. Sometimes it's more, sometimes it's less. But the nice thing there is you've got a pretty solid cohort of students that you're coming in with and that you're going to get to know over the course of 4 years of IIT physics, or however long it takes you, right? Now, about, I would say a little less than half of those physics majors will go on to kind of do a minor in, a major in astrophysics rather than just physics. And so astrophysics and physics undergrads will take a lot of similar courses, which I will kind of overview here. But the astrophysics majors, there are some other courses specific, more specifically focused on like astrophysics, like planetary, I think planetary astrophysics is one of them, stellar astrophysics, and then some other ones. I'm not an astrophysicist, so I know less about that. But if you want to know more about that, I am happy to go over it with you guys. Okay. So, yeah, so that's the teacher situation. That's your, fellow student situation. Now let's just go over your required courses a little bit. So for the physics degree, you got a variety of different courses you got to take. And I don't know, from my perspective, some of this is just, a lot of this is your bread and butter physics courses that you are going to get as an undergrad, at most undergraduate BS physics degrees at other larger universities. I think the things that set IIT apart in this process is that, I mean, of other undergrad physics programs I have talked with professors about, ours is pretty rigorous and it really has a lot of emphases that you don't see in a lot of other programs. So one thing that I would highlight about IIT's course load here. So the computational aspect is something that's really stressed very strongly at IIT. And what you'll see is, in particular, there are 2 separate physics courses specifically devoted to computational physics. So there's kind of this Phys 240 computational science, which is kind of like intro to computational physics. And then there is Physics 440, which is kind of advanced computational physics. And I was just talking to some of the other undergrads who do research with me about this class, and they think it's really, really fun. It's very challenging, but super fun. So like one of the students in my group is working on, so there's a very common code called SRIM, which is used by many physicists to propagate heavy charged particles like protons through matter. And so this student, the teacher had suggested to him that he make up a new version of this code from scratch. Because the current version is coded in Fortran, which is this ancient language that really is not very easy to use. And so he said, well, try to do this thing that SRIM does, but in Python instead. And so, you know, as someone who's probably just like starting out in physics, it sounds a little scary and pretty advanced, but you know, by the time you go through, you know, 2 semesters of quantum, 2 semesters of electromagnetism, intro to computational science, you know, you start to get what you need to know to start taking on a fun project like this. And I was pretty impressed by what this student was able to do. So yeah, I think that's one thing I like to stress about the IIT undergrad physics program in terms of course loads. So you can see all of the courses that are required up here. Does anybody, do either of you have questions about the required courses that you see on the in the syllabus right here, right now?
What is the instrumentation lab?
Yeah, so yeah, that's a good question. So we have 2 kind of required lab courses. So there's the instrumentation lab, and then there's like advanced physics lab. So the instrumentation lab, you will get some experience using laboratory techniques that you may come across, you know, in the research context, whether it's physics or bio or chemistry or a lot of possibilities. So for example, reflectometers and spectrometers. So you want to, let me give you an example. So one of the labs that is done in instrumentation lab, this Physics 300, is measuring the transmission of different wavelengths of light through various types of samples, like liquid samples, solid samples that are semi-transparent. You know, if you want to quantify how much light is getting through some material, to better understand the physics properties of material, you might use a UV-vis spectrometer. It's a very, very common thing to use in a physics lab or in a chemistry lab. So you get some experience using that kind of instrumentation. And, you know, over the course of doing that class, you learn how to use a bunch of instruments. You learn how to conduct a laboratory experiment. You learn how to write lab reports and those kinds of things. So that's like what instrumentation lab is. Then advanced physics lab, you're gonna basically same idea, but with like more specialized equipment. So in particle physics, you know, something we try to do is to detect gamma rays and detect various kinds of radiation, like gamma rays, alpha rays, beta radiation. And we have specialized equipment to help us with each of those tasks. You'll learn how to use the different types of radiation measurement devices. So, you know, like a gamma spectrometer, an alpha spectrometer, those types of things. Or you may learn to use other types of instrumentation that's useful in other fields, like material science. Oftentimes, you might want to develop some kind of thin films or to deposit some thin films on something and then measure their properties. That's basically what material science and condensed matter physics is kind of all about. So in our lab, we have atomic layer deposition chambers, and then we have X-ray diffraction machines to do experiments on the thin films that you actually manufacture in the atomic layer deposition chambers. So I know I'm kind of throwing a lot of jargon at you here, but that's the general idea behind these labs, to gain some familiarity with, some common and some more advanced types of physics equipment you might run across in particle physics, condensed matter physics, and so on and so forth. Does that answer your question?
Yes, thank you.
Sweet. Leah, did you have any questions up to this point so far?
I'm good.
Okay, great. Now, another thing I'll point out is, in addition to these required courses, there are also, there's also what they are called technical elective requirements. So basically what that means is there are physics courses that we teach that are kind of more specialized or devoted to a specific research topic. So for example, I'm a particle physicist. I study neutrinos. I build neutrino detectors. But there are other people at IIT who study muon physics and are interested in detecting the products of muons. All of that is covered in an advanced undergrad level course called subatomic physics. So in subatomic physics, you'll learn about some of the fundamentals of particle physics and nuclear physics. So that would satisfy a class like that. If you're somebody who's, seems like they might be interested in nuclear or particle physics, maybe that 3 credit hours you spend taking subatomic physics, which I think is offered every other year. If relativity is something that you think is really cool and interesting, we teach a relativity course either once a year or once every 3 semesters. If material science is your thing, there is a synchrotron radiation course. There are advanced undergrad condensed matter physics course that is available. And I'm trying to think of, biophysics. There's an upper level undergrad course in biophysics, which is kind of the physics of how, cells work and stuff. That's not my specialty, so I'm less good at describing what it is, but yeah. So that is the technical elective requirement. Now, do you guys have any questions about kind of upper level courses that you might be like, oh, do you have this that you might be interested in? Yeah.
Not that I can think of right now.
Okay.
Yeah, I don't think I have any of the right questions to ask. What are some things I guess you could brag about for your upper level physics courses?
Yeah, I mean, the things that I would brag about are, you're going to have upper level, if you go to some other school, some other undergrad institution and do a physics major, you're gonna have, you're gonna be able to take a subatomic physics course. You're gonna be able to take a nuclear physics course. You're gonna be able to take a biophysics course. And the things that I would say I would brag about is not that those classes exist and you can take them, because you can do that many places. The thing that I would brag about in terms of upper level undergrads is the research engagement that our undergrad students have. And I haven't really talked about that yet. So a lot of our students engage in undergraduate research during the semester with professors who are research active in the department. So yeah, just off the top of my head, I am aware of at least 6 of our 15 professors who are, no, sorry, it's more than that. It's maybe 8 of our professors who are, research active with undergrads throughout the year. So if you're somebody who is interested in kind of getting that enrichment beyond what your physics course load is here, the professors, it's a very tight-knit group of professors and a relatively small undergrad population, such that we're talking all the time, right? You're going to be coming to my office, you're going to be asking me questions, you're going to be or maybe you got your favorite professor in some other field or some other favorite professor from your class, ask them what they're doing for their research. And, you know, during the semester, we're doing research. During the summer, we're doing research. And get engaged in laboratory work outside the scope of some of these more lab-focused courses, like your instrumentation lab, like your advanced physics lab, or like your computational physics course. If you want a little bit more than that, if you want to get to know your professors, if you want to get a feeling for what doing research is like, which a lot of physicists do, IIT is perfect for that because of that combination of a large number of research active faculty and the relatively small undergrad population. Like if you want to get involved in research at IIT, you're going to have no problem achieving that. So I guess that is what I would really brag about. And I'm happy to brag more if you want me to, but I suspect you may have more specific questions about that kind of thing. Any more specific questions about that?
I'm not sure if they have any more. I'm not sure if you could maybe talk a little bit about like Argon and Fermilab within the context of research for them, that may be helpful.
Yes, that is very true. So when I say kind of on-campus research, that means working with an IIT research professor. Now, that doesn't mean that it's at IIT necessarily. I have had students who have, over the summer, gone to Fermilab and worked on existing experiments at Fermilab. The professors at IIT have very, very close ties to both Fermilab physics programs and experiments and efforts on Argonne National Laboratory. Now, raise your hand if you have heard of Fermilab or Argonne National Lab, either one. Or say, oh yeah, okay, so wonderful. Jacob has heard of Fermilab and Argonne. Leah, are you familiar with those places?
No, I'm not.
Okay, cool. So Fermilab is, where are you guys from, by the way? Are you Chicago local or are you from elsewhere in the country?
I'm from an hour away from Chicago.
Oh, okay, cool. And Jacob, are you Chicago area?
I'm from Akron, Ohio.
Ah, okay. So yeah, so Leah and Jacob in the immediate vicinity of Chicago, right in the suburbs, there are two of our national research laboratories. And over the course of the United States, there are like, golly, maybe 20 national laboratories. And these laboratories, their purpose is to do fundamental and applied science research. And a lot of the research is dedicated to like developing new energy sources. Argonne National Laboratory, they spend a lot of time developing new energy sources, developing advanced materials that may be useful for energy applications or other stuff like that, or just basic science. So in particular, Fermilab is the only national laboratory that is specifically dedicated only to fundamental particle physics research. And so needless to say, those places are great places that are going to have lots of science facilities that universities just don't have the resources to have. So in particular, Fermilab has the most powerful proton accelerator in the United States. And that most powerful proton accelerator is really useful for doing basic science experiments. In particular, you take a proton, you smash it into a target, and then neutrinos come out. And so you have a neutrino beam, so you can study the fundamental properties of these neutrino guys, which are some of the most basic fundamental particles that exist in the universe that we don't know that much about. At Argonne National Laboratory, they have the Advanced Photon Source, which is basically like the greatest X-ray diffractometer in the entire United States. So if you want to make some new material and learn about its properties, you take it to the Advanced Photon Source, You shoot a bunch of X-rays through it, watch the angles that they bounce off at, and that'll tell you the structure of that material that you just made and some of its properties. An example of this, Professor Segre's group uses the advanced photon source to characterize new battery materials. And so what Professor Segre is looking to do is find battery materials that can store energy more densely and recharge more efficiently than existing commercial batteries. And so what his group does is they charge up their battery, then they put that thing in their X-ray beam, and then they look at the structure of the material when it's all charged up. And then they drain the battery. Then they look at the material again. Then they charge it back up. Then they look at the material again with the X-ray to see how similar their material is after multiple charges, right? One of the important things about battery is how much of their charge do they keep after the 1,000th time recharging it. Here, they can look at the actual atomic structure to figure out exactly why the material that they're testing isn't recharging as well as it should, for example. So yeah, that I went a little bit of a spiel there, so I apologize, but I just am trying to emphasize that the research we do is really highly leveraged by being able to work with the national laboratories. And that means you can work at the national laboratories on research work if you want to. Other questions you guys have about, let's talk about research. So any research questions you have, like what does that look like? How do I fit it in with my classes? What do we do during the summer? Like what kind of questions do you guys have?
Is it hard balancing research and your classes?
So that's a really, really good question. It really depends on the student. Actually, students recently, like especially during COVID times when, life is just generally more stressful. What has ended up happening with the students that work with me, at least, is the students have said, this semester, I think I'm just going to pull back and I'm going to focus on my classes. And then during the summer, when I don't have classes, I'm going to get in some time for research. So in particular, 2 of the students that I work with told me that this semester. So they're just not going to do research semester. That's fine. Focus on their classes. That makes sense. But these same students, like before the pandemic, had time to put in, 5 to 10 hours of like doing research related stuff during the semester, and it's kind of just, it's more or less like a volunteer activity just to gain experience. So you can do as much or as little as you want during the semester. And professors are like going to be accepting of that, no matter how much or how little you choose. So I've worked with students who don't do any research during the school year. I've worked with students who've done a ton of research during the school year. It just depends on, how much stuff you got going on in the semester. Now, the optimal time to gain research experience, if that's what you want, is to do that over the summer. Because over the summer, you're not taking classes, so it's perfect, right? And so I have had a number of students. Usually I have 3 to 4 students working with me over the summer, any given summer. And during the summers, I actually provide students a stipend to do research. Because in theory, you're doing this in lieu of like taking on some kind of part-time summer work or something like that. So I should pay you. And other professors have research funding to do that kind of thing as well. So I guess that's a long-winded answer. The summary of that is, depending on who you are, you may do as much or as little research as you want during the semester, but summer is the optimal time to really get involved and get your feet wet doing that kind of thing.
I had a question less about the students, but more about just for you being a particle physicist. What can you explain to me about the Muon G2 experiment?
Ooh, so Leah, have you heard about this at all? This Muon G-2 thing?
Not yet, no.
Okay, yeah. So the only reason I ask is because it's one of these physics results that's actually made the crossover to like an article in the New York Times and other like media. Will, did you hear about this? I know you're not desiring to be a physicist in the future, but did you hear about this muon thing?
I have unfortunately not caught this one, and it apparently
Okay.
hasn't worked its way into my news.
So yeah, so muon G-2. So let me just bring up just an intro slide. What is a muon? So there's an experiment at Fermilab that studies muons and the fundamental properties of muons. What is a muon? So basically, most of the stuff we know of in the universe is made of these different particles. So you can think of this table of stuff, you can kind of think about it like the periodic table, right? So the periodic table, it's got a bunch of different elements in it. And in that table, we have all the elements that make up like all the stuff on Earth, right? So this is like another periodic table. It's a periodic table of all the subatomic particles that make up all the larger composite particles in the universe. So for example, all nuclei, every atom's got a nucleus. Every nucleus in every atom is made of up and down quarks. Every atom is made of a nucleus and an electron, or any number of electrons circling around the nucleus. Light that you see, that you use to see in the dark, and heat that is released from your skin as you just go about your day living. Those are all photons. Light is a photon. Heat is a kind of photon. And that's this guy right here. So you're familiar with some of the basic things in this like more fundamental periodic table of all of the subatomic particles. So I just named some ones that those are the ones I circle in red here. The muon is right here. It's basically a heavy version of an electron. And they exist kind of much more rarely than like electrons and up and down quarks on Earth. The main place you find muons on Earth is in our atmosphere. Our atmosphere is constantly bombarded by cosmic rays just coming from various places in outer space. And when those cosmic rays hit our atmosphere, they have crazy interactions, and then in some of those interactions, you make these little muons, these heavy electrons. Now, there is 2 places on Earth where humans have made beams of particles specifically to make a large number of muons, these guys here. There's one place in Switzerland, and there's Fermilab. And remember, Fermilab is this place that's out in the Chicago suburbs, right? So my grad students do research at Fermilab. Okay, they don't work on muon G-2. They don't work on studying these muons, but okay. You might chat with some undergrads who do when you go there over the summer or something. Okay, so these muons, one of the things we want to do is study their basic properties. And one of their basic properties of muons is all subatomic particles kind of spin about their central axis. Classically speaking, every one of these particles here on this table spins around in a certain way. And in E&M, in your second semester E&M course at IIT, you will learn that if a charged object is moving, it's creating a magnetic field. And so a muon is charged and it's spinning, so it's moving. So it has some kind of magnetic field that it creates, which interacts with with its surroundings. And this muon G-2 anomaly is basically learning how this muon interacts with the world around it by decaying. So when muons interact with the world around it, they end up breaking into smaller parts. And if that muon breaks into smaller parts, more quickly or more quickly than you might predict, that means that there may be more stuff around interacting with muons than you knew about. So what this G-2 experiment did is it measured how quickly its beam of muons decayed, and then it decayed a little bit more faster than our basic theory of all of this stuff predicted. So we don't know why. And anytime in particle physics something happens and you don't know why, that's really, really exciting. So is that a halfway decent explanation for you, Jacob?
Yeah, certainly much more easy to understand than the ones that Brett Weinstein posted.
Who's,
I don't know if you.
Yeah, and I was surprised at how there's been a lot of like pop science descriptions out there that are pretty good, but it's hard to explain. These basically they're measuring this decay rate of this muon to like a part in in like a very tiny fraction. You're measuring the decay rate to be like, I don't know, I'm just making up a number here, but like decays in like 0.5 microseconds plus or minus 0.0000001 microsecond or something like that. It's crazy how precise these experiments are, and you're looking for just these tiny inaccuracies in these fundamental properties of these particles. I guess that's just a testament to like how good our particle physics science has been up to this point, that we're now digging at little tiny parts per million problems to find new physics. But yeah, my research, and actually the research of 2 or 3 other professors at IIT, is related to studying not the fundamental properties of this guy here, but of these guys in purple here. These are called neutrinos. Neutrino you can basically just think of as an electron that has no electric charge and almost no mass. So they're really, really hard to detect, but Fermilab is the preeminent neutrino, has the most prominent neutrino source in the world, basically. And so if you are interested in particle physics and neutrino physics or muon physics, man, you should come to IIT because you'll have some opportunities to do undergrad research about those things. Other research-related questions, Leah or Jacob?
None that I have. Any other information that you have to share?
Cool. Yeah, and one thing I wanted to just do very briefly, I am me, so I'm biased to talk about my stuff. So one thing I want to do to give you a little bit better view of just the department at large is, and just physics at large, I guess. So this is just to give you a sense of what other people at IIT study and what their specialties are, because that's something that also sets IIT apart, right? We have our own people, and our people has specific specialties that is going to set us apart from other universities, right? So to illustrate this, one thing I'm showing you, this is just a bunch of screenshots from the American Physical Society website. And here it just shows you a whole bunch of the various divisions of the American Physical Society that exist. That's just another way of saying, here is all the different categories of physics that people study. So you can see there's a big list of stuff. And if you go to IIT and you take your first semester intro to the profession class, we'll get into way more detail about what all of these different topics are and what they encompass. Just like, for example, the Atomic, Molecular, and Optical Physics division and the Laser Science division of APS, it's lasers, right? It's frickin' lasers. Trapping atoms with lasers for many possible reasons. Maybe you want to study some fundamental physics process. Maybe you want to make some crazy Bose-Einstein condensates and study those, whatever. That's what those divisions are about, is using lasers to do fun stuff, right? whatever, astrophysics, you know, that's the cosmos. Like what is out there today in the cosmos, and what did the beginning of the universe look like, and what was around at the beginning of the universe, right? Yeah, blah, 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 blah. So there's a bunch of different topics. But what I want to kind of highlight is at IIT, there we go. The fields we have covered really well are the ones that I have like circled here. So let me see if I have, yeah, okay. So astrophysics, as I said, we have an entire major devoted to astrophysics. So if you like astrophysics, if you like figuring what's out there in the cosmos currently and what was there at the beginning of the universe and everything in between, astrophysics is for you. We got that covered. Biological physics, soft matter, I would kind of lump those two together. That's basically studying cells and like soft matter. So like tissue, muscles, cell membranes, DNA, that kind of stuff. Maybe you want to understand one of the things that one of the professors studies in our department that I think is super cool is we have cells. Our body are made of cells, and you know, stuff has to get into our cells. So for example, viruses have to attach to cell walls and stick their RNA into our cells so that they can like get the cell to reproduce it. One of the professors in our department studies the physics of how that virus sticks its RNA through the cell wall. Like, what's the physics of that? There's a whole bunch of physics. There's like E&M in there. There's statistical mechanics in there. And one of the guys does experiments about this kind of thing. And one of the guys uses complex computational modeling to study this topic. So that also kind of sticks computational physics in the mix as well. Condensed matter physics, I kind of already talked about that. Like, you know, the APS at Argonne National Laboratory is the perfect place to study condensed matter. That's basically, let's make a metal, let's make an insulator that we want to do some special thing, have some special physical properties, and then let's shoot X-rays at it. Let's shoot electrons at it. Let's shoot neutrons at it to study the properties of that material. We have some very solid research coverage of that at IIT. Material science, okay, that's the same thing. Or not, I shouldn't say that. If there was another physicist here, they'd yell at me, but you get the idea. And then nuclear physics, particles and particles and fields, that's nuclear and particle physics. I kind of already talked about that before. Let's understand the properties of nuclei and the properties of those fundamental subatomic particles in the universe. And then the physics of beams. We have a very good specialty on beam physics at IIT, which is basically how do we make those strong X-ray sources at Argonne? How do we make that crazy proton beam, that one-of-a-kind crazy proton beam we have at Fermilab? It takes a whole lot of physics to get a lot of protons, which, you know, they all repel each other, right? So try to stick those things as close as possible to one another and then get them all to have the same exact energy and hit the same target in a very, very small area so that you can do the physics you want to do. It's not easy. There's a lot of problems involved, and beam physics is basically studying all those problems to try and develop better electron and proton beams. Or muon beams in the case of G-2. So that, I think, gives a better view from not just my perspective as a particle physicist at IIT, but more general view of what all of us at IIT as professors are interested in. Oh, and one other thing I do want to mention, you guys care about more than just professors, right? You're students. So you're like, well, what are the students doing? What research are the students doing? So I guess I would say over the course of the past 8 years at IIT, like I said, I've had 2 to 3 to 4 IIT undergrads working with me over the summer, every summer. And there are many other professors who do the same thing. Of the students that have worked with me, I have had 1, 2, 3, 4, 5, 6, 7. 7 of those students have been co-authors on scientific publications by the time that they left with their BSs. So it's not just like you're gaining experience, you're also could be an author on a published paper as a result of coming to IIT and doing stuff. I'm not the only professor that that's the case for, I assure you. So yeah, it's kind of fun to think about being a part of that kind of thing as an undergraduate physics researcher. Okay. Other questions you guys might have, whether it's classes, student life, research, whatever. Any other questions?
Could you go more into the astrophysics department?
Yes. Give me a moment because I want to bring up the course catalog because I want to just illustrate for you explicitly the difference in what the curriculum is there. So just give me one moment to bring that up. There it is. Okay. So I'll have these side by side and then I can show you them to you. Okay. So here's the Bachelor in Astrophysics. So here you are. See, here is, so the primary difference between physics and astrophysics majors is this lump of stuff right here. As an astronomy student, sorry, and it's astronomy, yeah, a bachelor's of science in astrophysics. So in order to be astrophysics, you got to cover your astronomy bases and you got to cover your physics bases. So you'll see there's still a whole lot of physics requirements, right? You got many of these you'll see overlapping with our physics major courses. But you'll see some things have dropped out, right? Like the computational physics course is not in there. I think you can take out one semester of quantum and one semester of electricity and magnetism, and there's some other differences. But in return, you get all these fun astrophysics courses, right? Intro to Astrophysics, Observational Astrophysics, Relativity, Stellar Astrophysics, and Extragalactic Astrophysics. So just to, okay, Intro to Astrophysics, whatever, that's your survey course. Observational Astrophysics, that's basically, how do I use a telescope? And what is the variety of ways that I can look at stuff in the sky and learn more? So that, I'd think about optical astronomy. Maybe you talk about astronomy in the different wavelengths, right? Like optical astronomy, X-ray astronomy, that kind of, and just discussing the difference between those things. And what do you learn by looking at those different realms of astrophysics space? Relativity, okay, relativity, right? Einstein, time dilation, yada, 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 right? Stellar astrophysics, how do stars work? Extragalactic astrophysics, that's, okay, what are black holes? What is what is the origin of the universe, right? Talk about what is cosmology? How did we know what the beginning of the universe is like? Those kinds of things. So it's a lot of fun topics in there for sure, even just for 5 classes. Yeah, and I'd say, yeah, those are basically the primary differences. And we have 2 professors who kind of lead this astronomy, the astrophysics major emphasis. And so a lot of the courses you'll take from these astro-focused professors. Those professors have really good connections to the Adler Planetarium. And actually some of the Adler Planetarium folks actually end up teaching some of these courses sometimes. And really good connections to other programs in the Chicago area. So for example, a number of the IIT astrophysics students have done summer research at the Northwestern's Sierra Center, which is an interdisciplinary astrophysics research group at Northwestern. So it's like you're doing your IIT degree, and then in the summer you go up to Northwestern and together with a group of undergrads have a dedicated astrophysics research project that you work on. So that's a little more about the astrophysics major. Did you have other specific questions about that, Leah?
Is there any research going on with that at IIT, or is it just like with the other places as well?
So in terms of research, none of our research active professors are super focused on astrophysics research. So that is, I guess I would say that is one drawback. But like I said, that is easily made up for by these connections we have to other institutions in the Chicagoland area, like Adler. I mean, Adler, you can't be an undergrad at Adler, right? So you need to be if you're interested in being at Adler and working with these scientists at Adler, you gotta be hooked up with a university professor who is doing research or just acquainted with these folks at the Adler. I think we've had, over the years, we've had 3 graduate students at IIT get their PhDs with advisors at the Adler Planetarium. And one of those people is probably going to be joining the faculty not so long from now. Other questions, Leah? That's a good question.
That's it. Thank you.
Cool. Jacob, you got other questions?
I see you're on a MacBook. I was wondering what drawbacks to having a MacBook are and that you see with students in majoring in physics, or if Windows would be optimal.
I think you can make anything work. One thing I will note is like a lot of the folks in the computational physics courses, they won't use their laptops. We have a computer lab in the physics building. So we have the Pritzker Science Center, which is where the physics classes are. Most of the physics professors are on the first floor of that building, and one of the rooms on that first floor of Pritzker is a lab, a computer lab that's specifically dedicated to having all the software needed to do all sorts of different projects for your computational courses and other courses. So to a certain extent, it doesn't matter what kind of machine you've got. You've always got the computer lab there if you need it. But I mean, it doesn't really matter is the short answer, because regardless of what research group you want to work with, there's a way to get your machine to do what you need to do. If you have a Windows machine, chances are you're going to install some kind of virtual Linux machine inside of your Linux machine, inside of your Windows machine, so that you can run your various physics programs on a Linux system. If you have a Mac is Unix based, so that's just not any problem at all. So the short answer is it really doesn't matter. There's good tools on Windows machines and Linux machines and Macs to make you adaptable. It's a good question, though.
Another question I had is, about a year ago, I think, Chicago had the huge conference about the quantum network. I was wondering
Yes.
what Illinois Tech has done with that and how that's progressed.
Yes. So funny that you ask. In like less than I think maybe a month or so, IIT is having a dedicated day-long workshop to introduce a lot of our advanced undergrads and grad students and comp sci undergrads to basic quantum computing concepts. So it's basically like a quantum computing tutorial workshop where like some folks from IBM are going to be there. We just hired a quantum information science focused professor, Professor Rakshakatiwada, who is going to help lead that, and along with some other professors in the Chicago area. So if you want to go to that, I can send you the registration information, and it might be just a fun kind of first look at what this quantum information, quantum computing stuff is all about. So just let me know if you want me to send you more information about that, and I totally can. It's like I'm gonna go because I don't know that much about quantum computing myself, and I'm kind of interested to learn how easy it is. My understanding is it's actually really easy to just write up your first quantum computing program and submit it to run on one of the quantum computers that IBM has made available to the public. So that sounds kind of fun to me. I'm kind of excited about it. So yeah, so that's that. In terms of the quantum network research, that's like a very specific branch of quantum computing research. IIT doesn't currently have a professor that works on that specific project. What IIT professor, this Professor Katiwada that I was talking about, her specialty is in readout of quantum computers. So how do you take the qubits and you run some operation on your qubits, and then you got to read out the information somehow and do something with it. So Professor Katiwada's emphasis is being able to read those qubits and program them. What's the physical process that you use to manipulate those qubits? That's her specialty, and that's like another piece of the quantum computing chain, right? You gotta have stable qubits. You gotta have ways to manipulate the qubits. You gotta have ways to send the information outside of your quantum computer to places far away. That's the quantum networking part. That's a really good question, though. But yeah, so IIT, I mean, I would say 5 years ago, I would say you're kind of out of luck if you're interested in quantum computing. But, you know, now that is totally not the case. And yeah, if you're interested in quantum computing, IIT is a good place to be. So I am being notified by my daughter that it's dinner time. So I am apologize, but I must leave you guys.
Thank you so much for helping out. That was very helpful for me to learn about physics. I think it's always great when I get to sit in these sessions. And I will tell the students, I've gotten a chance to visit Argonne and walk the ring, and it's an amazing facility. It's really cool to hear that work and to hear a little bit more about, you know, how it works and what's happening there is kind of nice as well. So
yeah, and by the way, if you take in that intro to the profession class I talked about, with next fall, you know, God willing, with COVID, one of the activities that we do for ITP, that Physics 100 course, is we go to Argonne National Lab, we go to Fermilab, and we go just check it out and get a tour and see what's going on and talk to some of the scientists. So yeah, thanks very much for chatting, guys. Please send along my contact information to Leah and Jacob. If you guys have further questions, I'm happy to chat with you guys.
Awesome. Well, thank you so much. I'm happy to stay on and answer any admissions questions as well. I know you're going to head out, but if you have other questions, I'm